Thank you, everyone. Welcome. I appreciate you taking the time to join. As Ron mentioned, I'm going to be talking about the performance benefits of sparse models. By way of introduction, I work at Numenta, which is a research company headquartered in the Bay Area. And our mission is really to sort of understand the human neocortex and then take those insights and apply them to AI. Before we dive into the details, everyone probably knows this, but it's never hurts to have a refresher. Let's go through what actually constitutes an artificial neural network. It's composed of what we term point neurons. These point neurons basically form a weighted sum of their inputs, and it's these weights that we learn during training. That weighted sum is then potentially subject to a nonlinear function like a ReLU. These neurons are arranged in layers, and there may be multiple layers in your network with the outputs of the neurons in one layer feeding into the inputs of the neurons in the next layer. And so you can see on the left-hand side, we apply our inputs, be that an image, be that our tokens from NLP, whatever that may be. We apply it to layer one, we compute the outputs from layer one, those become the inputs to layer two, and so on and so forth until we get to our output. These neurons, these artificial neural networks are termed dense fully connected. And what that means is each neuron basically gets an input from each and every activation that's incoming, right? They're fully connected to all the activations. And we typically formulate the computation of a layer of neurons as a matrix multiplication operation. You can see here that we have the neuron weights and they compose one matrix. We have an activation vector. This may become a matrix itself if we have a batch size larger than one. So if we're processing multiple activations at a single go, this then becomes a matrix itself. And basically, we're performing a matrix multiplication to get the results. As you can expect, as we add more and more neurons to each layer, as we add more and more layers to the network, this becomes, pretty computationally expensive, not only to train these neural nets, but even just running inference on these neural nets. So what have we done to basically address that problem? Well, to date, we've really got very, very good at performing matrix multiplications extremely quickly. And it's really this abundance of compute that really has allowed deep neural nets to sort of, proliferate to the extent they have over the last number of years. And GPUs have really become the workhorses of AI, especially in the training arena, but even increasingly so on the inference side of the house. Some of the high-end cards can perform, in excess of 500 trillion arithmetic operations every second. And, that number is increasing with every subsequent hardware generation.
I'm sorry.
That said...
I'm sorry to interrupt. We have had a request that showing multiple slides on a screen is too small to view.
Oh, sorry, you're not sync. Sorry, I thought you were.
Thank you.
All right. Is that better?
Is that better?
Yep.
Please enter in the text in the chat, please. Cool. Okay.
All right. Sorry about that. My apologies. Where was I? Yeah. So basically, even though we have this abundance of compute, it's really hard for hardware to keep pace with the explosive growth of models, right? If we look at, say, the transformer space, which really sprung to prominence a few years ago, initially in NLP, but now people are starting to apply transformers to the vision space as well. The initial set of transformers had, less than 100 million parameters, whereas some of the newer versions have, in excess of 2 trillion parameters. So really an exponential increase in the size and complexity of these models. I mean, they're delivering better results, but nevertheless, they're extremely costly to handle, and it can take multiple GPUs, many hours, days, or even weeks to train these networks. As some concrete examples, BERT back in 2018, which really galvanized attention on the space, is estimated to have cost about $6,000 to train. Fast forward to 2020, you have GPT-3, which is not the biggest by any means, but really sort of captivated attention, and there was a lot of hype around this model. Is estimated to have cost in excess of $10 million. So this is really starting to hinder progress. It's really making it such that only large organizations can actually afford to train some of these models. So what can we do about this? Well, from Numenta's perspective, we look to the human brain to help us understand what we can be doing better. We can't multiply 64-bit numbers particularly well, us humans, but nevertheless, we're pretty smart, we're pretty versatile, we do a lot of different tasks pretty well, and truth be told, we still leave most AI solutions in the dust today, and we do so with an incredibly constrained power budget. The brain is burning around about 20 watts. So if we look at an artificial neural network and compare it with, the human neocortex, a number of things become immediately apparent. As I mentioned, in the artificial neural network, basically they're dense, fully interconnected neurons. In contrast that with the brain, neurons interconnections are extremely sparse. There's a lot of neurons in the brain. Each neuron is only connected to a small fraction of the total neurons. If we look at artificial neural networks, we can see that activations are pretty dense. You get some sparsity in the activations from the ReLU, but nevertheless, there's large numbers of neurons at each layer that get activated. Again, contrast this with the brain. Even if you're thinking about something really, really hard, it's only a couple of % of neurons that are actually active at any given time. If we look at the point neuron as well, it is a very basic abstraction. It's a very, very simple neuron. There's a lot of subtlety and elegance in biological neurons that is just completely missing from artificial abstractions at present. And then last but not least, we can learn from very few examples. You can give a small child a picture of a tiger and they're able to, classify tigers, identify tigers. You don't need to show them 10,000 images of tigers, rotated, flipped, zoomed with different backgrounds, with different lighting conditions. It really illustrates the sort of very basic brute force techniques that we're currently using to actually train our deep learning models. So we've been looking at this, trying to unlock the secrets of the neocortex, and now we're in the process of trying to apply these to different aspects of AI. Today, I'm just going to be talking about the first component that we've been looking at, which is sparsity. So I mentioned the brain is sparse. We can also make today's deep neural net sparse. We can do it in two main ways. We can limit the interconnections between the neurons, which is called weight sparsity, and we can limit the number of neurons that can become active at any given time. This is called activation sparsity. You can see that I'm doing this in this example here, right? On the activations on the left-hand side, I've made x2 0. And then you can see previously each neuron was fully connected. It was connected to all 4 inputs. Now they're each only connected to 2. And there's a nice benefit to this. When you start to look at the weight matrix here, you can see that for every missing interconnection, that we actually represent that with a 0. Similarly, in the activation matrix, every time we have an inactive neuron, we represent that with a 0. And given that 0 multiplied by anything is 0, this actually allows us to skip computing a lot of the subproducts associated with the matrix multiplication. It makes the computation of the output of the neuron significantly simpler. And you can see that as an example here, right? This is output Y1. Previously, there were 4, subproducts that I had to compute. Now I'm down to 1. So basically, once you start to embrace sparsity, you can achieve significant computational savings. How much benefit can we get? Well, that really depends on the degree of sparsity, right? So if we look here, you can see on the, I guess the x-axis is 3D, but on this axis here, we have weight sparsity. If you go to about 90% weight sparsity, basically, 90% of the elements in your matrix are now 0. You've reduced the amount of compute that's required by about 10x. You can do the same thing with activation sparsity. And what's cool is you can even combine them. Right, weight sparsity is introducing zeros into the weight matrix. Activation sparsity is introducing zeros into the activation matrix. And so you get a multiplicative effect. So if I have 90% weight sparsity, 90% activation sparsity, I've actually reduced my computational overhead by a factor of 100. And so, significant opportunity to improve the performance of these networks. So how do you go about doing that? Well, there's 2 main approaches. You can think about training a sparse network from scratch, or what is most common today is actually you can create a sparse network from an existing dense network. So you train a dense network, and then basically you remove some of the less useful interconnections to create a sparse network from it. You can do this as a sort of, single pass operation, but that typically leads to a less accurate solution. Most of the solutions out there today are iterative. So basically what you do is you take your dense network, or you take your network, you look to see which are the least important weights and use some metric to judge importance. You remove some fraction. Removing that fraction impacts the accuracy of the neural net. So you then have to sort of retrain it, fine tune it a little bit to allow it to recover that accuracy. And then you iterate, removing a few percent at a time until you get to your desired sparsity. There's a variety of different ways by which you can judge an importance of an interconnection, but most simply and used in a lot of situations is just the magnitude of the associated weights. There's a variety of different techniques. Some are more sophisticated. Some not only remove weights, some will try to regrow them, really trying to figure out what the optimal set of sparse connections is to deliver the best possible accuracy. Most of attention today is focused on weight sparsity, but you can also do activation sparsity, as I mentioned as well. And there's a couple of simple techniques for that as well. Basically, at each layer, you can look at the activations, basically sort them by magnitude, if you will, and then take the top K. Those neurons are allowed to become active. Everything else is set to 0. Or a simpler technique is basically thresholded ReLU, in which you apply a threshold and say something like, everything below 0.7 is actually 0. And what have you. This is a little bit more of a noisy technique because obviously, the exact values of the activations is dictated by the input image. And so you're never precisely able to control how many activations are going to occur. Nevertheless, this is actually a sort of very simple local threshold you're applying versus having to sort all of the activations in a given layer to figure out the top K. A simple example here, a lot of what people use today is what's called gradual magnitude pruning. It's an iterative technique, and we're using the magnitude of the weights to determine what needs to be removed. Typically, you set it up, and then there's some number of pruning events interspersed with, retraining to allow the accuracy of the network to recover. You can see an example of that here. I'm sort of basically pruning a tiny BERT here. On the right-hand side, you can see that over time, the sparsity is increasing, but I'm doing so in a nonlinear manner. Also on the left-hand side, you can see that basically, removing these weights does cause accuracy to regress. But, as I train over time, I can recover the vast majority of that accuracy. So the question now becomes, how sparse can I make my networks? Well, the first thing to note is it is possible to create sparse networks with identical or equivalent accuracy to the standard dense network that you're starting with. You don't have to sacrifice accuracy because of sparsity. The degree of sparsity that you can achieve is, very situation dependent. It's going to depend on the sophistication of your pruning algorithm. It's going to depend on the network that you're using. Certain networks have a lot more of a parameterization than others, and you can safely remove, a much greater proportion of the weights from the dense network. And also in many cases as well, some people will choose to make the determination that, I'll trade a little bit of accuracy to get my sparsity that little bit higher, right? The higher the sparsity, the great, the greater the amount of computational overhead that we've removed. And so hopefully we'll get a faster neural net at the end of it. And so maybe you're willing to trade some accuracy for performance. As some examples of how sparse you can make networks, this is some of the work that we've been doing. This CNN is a convolutional neural net. It's a fairly simple one. It's got 2 conv layers and 1 linear layer, and here we're able to take it to over 90% sparsity while retaining the accuracy of the original dense network. I'm sure everyone's familiar with ResNet, which are used in the vision space. Here again, we can take this to over 75% sparse very easily while retaining the accuracy of the original dense network. And then most recently, we've been looking at BERT. Here we show BERT base. We can basically take it up to, somewhere between 85 and 90% sparse without losing any accuracy. So basically, the upshot of this is, we're not talking here about removing 5 or 10% of the weights, right? We're talking about removing the vast majority of weights. And so we should be able to get a significant performance improvement as a result of that. All right, so we've talked about the potential for speedups, right? We've talked about the simplification of the computation that's being done. That said, there are some challenges with actually realizing that performance gain on today's hardware. So today's hardware, as you guys know, basically thrives on dense, regular, predictable compute. It takes a while to move data from the memory into the core. And so it makes sense that you want to be able to understand and predict your data accesses far in advance, allowing prefetchers to move that data in a timely manner. Most processors today also support some form of vector SIMD processing. And so this dense structure allows you to process multiple elements in parallel. Dense matrix multiplies fit this perfectly. And, on GPUs or CPUs, dense matrix multiplications absolutely scream, right? You get incredible performance from them. If we think about what we've been doing when we've been introducing sparsity into our neural net, essentially what we've been doing is, we've been looking at the least important weights and we've been removing those, right? And so you might expect that the pattern or the location of these zero weights and the locations of the remaining non-zeros, if you will, is fairly random. It's not going to have a very regular pattern. It's going to be fairly irregular. And unfortunately, when you end up with this irregular pattern, it's actually very hard for modern hardware to execute those sparse matrices very, very efficiently. In fact, sadly, in many cases, it's actually just faster to treat them as a dense network or a dense matrix and just multiply the zeros, as depressing as that sounds. That said, we can try and remedy this situation, and we can do so by trying to constrain the sparsity patterns that we're creating, basically creating rules and constraints on where the non-zero elements can actually be located in the matrix. So really, in essence, we're basically saying certain weights can be removed or certain interconnections can be removed, others can't. And by doing this, we hope to create patterns that are more amenable to today's hardware. There's a variety of different ways that you can do this. It's called structured sparsity. One way is rather than allowing just, single non-zeros to occur in isolation, you're going to force them to occur in blocks within the matrix. The other way is partition sparsity, where basically you take your matrix, you subdivide it into a number of partitions, and then you enforce sparsity requirements across each and every partition. The final one, complementary sparsity, is something that we've been developing at Numenta. And basically the idea here is you take multiple sparse entities and compress them into a single dense entity that can then be processed extremely efficiently by today's hardware. It should be apparent that you can apply these strategies in isolation or collectively, Basically, you can have a partitioning strategy, and within those partitions, you can do, block sparsity. It may seem a little strange that basically we're going to tell the network and say, hey, the non-zeros must occur in these groups or in these positions. But nevertheless, it is actually possible to train networks with minimal losses in accuracy while applying these kind of constraints. The network sort of learns to live and route information through these constraints that are being imposed. That said, there's a limit to the constraints that you can actually impose while retaining the accuracy. Obviously, you might want to grow your blocks as big as the width of a SIMD unit, right? That would make it run very efficiently on modern hardware. But once you start to get to blocks of that size, you're basically degrading accuracy. But there is a balance that can be struck where you can live with smaller block sizes that give you some of the benefits, but still retain a lot of the accuracy associated with unconstrained sparsity. When we're talking about sparse matrices, it's not that we're basically just having a dense representation with zero elements, and then the hardware in real time is trying to figure out where these zero elements are and skip them. Typically what we do is we take that matrix and we represent it in a sparse format. A couple of the common sparse formats are compressed sparse row and block compressed sparse row. And you can start to see here the challenges associated with processing these extremely fast on hardware. If we look at the compressed sparse row, we can see that in the data array, we have A, B, C. They are adjacent elements. Unfortunately, they don't correspond to adjacent elements in the sparse array, nor do they interact with adjacent elements in the activation matrix, which makes it hard to do sort of SIMD processing on them. equally to figure out where element A is in the sparse array, and to then determine which element in the activation array it actually interacts with, we have to interrogate these indices, the row pointers and the column offsets. And this introduces overhead, there's pointer chasing, it's indirection. And again, this is impacting the predictability of the memory accesses. And so you can quite easily see why this is eroding performance and why processors find it fairly difficult to actually process these things. It then also makes sense why block sparsity improves performance, because here we've introduced locality. We can maybe get some SIMD processing going. And also we've amortized all of this indirection now over a block of elements. From a partition standpoint, as I said, you basically divide your matrix into a bunch of subpartitions and then apply sparsity constraints independently. This distributes the sparsity more evenly, allowing it much more easily to be load balanced, to be basically split across multiple processing elements, and also reduces the scope of the memory accesses. And so you can see here that for all of these matrices here, this is a 75% sparse matrix. On the top left, you've got unstructured. So basically, it's a pretty random pattern. And then on the others, there's various different partitioning strategies you can apply. You can apply it in the X dimension, the Y dimension. You could apply it in both X, Y. And then within each partition, you can have, basically singleton sparse elements, or you can have blocks. And the blocks can be square or rectangular. And by imposing these constraints, we can actually recover performance and actually make it such that on today's hardware, we do get some performance benefits from sparsity. So we talked about, the performance benefits that exist, the fact that we should be able to run these things and compute these things a lot faster. We've talked about some of the hardware challenges. So where are we today? Well, I think that, sparse networks are really becoming more commonplace. It wasn't that long ago where they weren't really being discussed. They were more of a research topic. Today, I think they're really starting to enter into the mainstream because of the performance benefits associated with them. People are running them in operationalized setting. There's been a significant increase in the research that's going on into sparsity. People are looking at different ways of creating sparse networks, different techniques for running sparse networks fast, and research into sort of understanding the characteristics and the behavior of sparse networks. Today, as I mentioned, most of the focus is really on weight sparsity, and it makes sense, right? Your weights, especially at inference time, have been pre-computed. They're static. So basically, it's an offline process. You can examine the sparsity patterns. You can come up and synthesize code that takes advantage of that. For activation sparsity, this is now much more dynamic and is input dependent. And so you're forced at runtime to trying to make these determinations about where you want to impose sparsity that makes it much harder to exploit. Unfortunately, there is very little discussion of leveraging both weight and activation sparsity in combination. And this is something we're trying to change at Numenta, basically because there is so much performance opportunity. If you're really just looking at either of those dimensions, you're basically limited to maybe 10x. If you combine them, now we start to be able to get 2 orders of magnitude performance improvement from sparse networks. There's a lot of people out there at present who are building new hardware architectures for AI. For a lot of these architectures, they are making sparsity an explicit consideration. So these future generations of hardware should be able to run sparse networks significantly more efficiently than hardware can today. That said, even today on existing hardware on CPUs, GPUs, and FPGAs, you can get some meaningful speed ups from sparsity. And so let's look at some of those results. Before we dive into that, just a sort of list of various sparsity software resources. The good news is that there's a lot of software out there, a lot of open source software, a lot of open source libraries that make it super easy to actually go and create your own sparse networks. There's a nice library from Microsoft, another one from Intel. They support a wide variety of different pruning techniques, making it very easy to actually go and create these sparse networks. Once you've created a sparse network, you actually need to find something to run it on, an inference engine, a runtime that's actually going to take advantage of that sparsity. There's a couple of them out there today. There's one from Neural Magic that is very nice called Deep Sparse that runs them very fast, and also Apache TVM does a good job. So basically you can take your trained network, you export it as an ONNX file, and then once you're in the ONNX format, which is really a model interchange format, you can then choose to run it on these different inference engines. And then also, we're starting to see sparse networks even appear in model zoos. And so it may not be necessary to even really go and train them yourself. You basically go and find a sparse model in a model zoo, and then you're good to go to basically start using sparse models out of the gate. So let's look at the performance. Initially on CPUs, we're looking at weight sparsity here. We're referring back to that convolutional neural net that I mentioned, 2 conv layers, 1 linear layer. I've made it 95% weight sparse here, and I'm running it on a variety of different CPU inference engines. You can see that on Deep Sparse and TVM, we're getting between 2 and 3x performance improvement. Unfortunately, on the ONNX and the OpenVINO, which are actually fairly common and fairly well-supported runtimes, these runtimes don't even seem to bother to try and determine whether you're running a sparse model, and so there's no benefit to introducing sparsity. But on these other ones, we are starting to see, 2 to 3x performance gains. That said, it is 95% weight sparse, so I've removed, the vast majority of the weights. I should be able to get up to basically a 20x performance improvement from this, but we're only getting 2 to 3x. But still, nevertheless, it's a good start. In this plot here, I'm basically looking at a ResNet, and I'm using the Deep Sparse engine, and really just illustrate here that the performance gain that you achieve really does scale with the degree of sparsity. You can see here that if I've only introduced, a small degree of sparsity, 50%, 75%, I may get a performance regression compared to dense, or my performance gains may be very muted. So you really need to be able to sort of crank up that sparsity towards sort of, 90, 95%. To see significant performance benefits. You can also see here that the performance really varies by batch size, and there are certain magic numbers associated with a lot of these inference engines when you're performing sparse computations. And that's really because if you have a sparse weight matrix, varying the batch size, basically the number of rows in the activation matrix, there's certain software tricks you can play that make it much easier to perform that sparse dense computation. And so, typically it may be a multiple of the SIMD width of the processor, but you'll start to see certain magic numbers. For certain batch sizes, you may not see any performance benefit from sparsity, whereas some others you'll see a much bigger. So it's worth thinking about that once you're leveraging sparse networks. Here again, we're looking at Deep Sparse. We're looking at BERT base. Again, just to illustrate that even for large complex networks like BERT, you can get decent speed ups from leveraging sparsity. We're up to about 4x here. You can also see again that increasing the degree of sparsity increases your performance benefit. And you can also see here as well, this is the trade-off between accuracy and performance. Here for 80% sparse, the 80% sparse model is basically as accurate as the original dense model. If we go up to 95% sparse, we've lost a little bit of accuracy, but nevertheless, our performance has gone from 2x the dense network to 4x. And so that may be a parameter that people are willing to play with when they think about trying to improve the performance of their models. So we've talked about CPUs, what happens with GPUs. There's a bunch of different sparse libraries out there for GPUs. Unfortunately, most of them seem to be focused at HPC computations where the size of the matrix, the degree of sparsity, is somewhat different from what we see in neural nets. That said, NVIDIA in the most recent iteration of GPUs, I believe the Ampere GPUs, they've actually introduced dedicated hardware support for sparsity. It's pretty stringent requirements. They require 50% sparsity across 4 element partitions. And you can see that at the bottom here. Basically, we initially start off with a dense set of weights. We can then do our iterative pruning. Here, we've got partitions of 4 elements running in the X direction. And out of each 4, 2 of them can be non-zero. We again would fine tune the weights to recover the accuracy. And then we can store a compressed representation that can be basically taken advantage of by the hardware that they've introduced into this recent GPU. Given you're doing 50% sparsity, that's basically going to limit your performance uptick to about 2x. NVIDIA reports that for BERT inference, they're seeing about a 1.5x speed up, and for ResNets, they're seeing ResNet 50, you're seeing about a 1.3x performance gain. So again, pretty compelling speed ups given that you've got an upper bound of only 2x. So that's GPUs. I do want to talk a little bit about some of the work that we've been doing on FPGAs, and it's a technique called complementary sparsity. Typically with block sparsity, we've discussed there's a lot of indexing, a lot of indirection, a lot of overheads that really limits performance. We're trying to take a different approach with complementary sparsity, and basically the constraint that we're going to introduce here is that across sets of kernels or weights, the non-zero elements must not overlap. And you can see that shown here, right? Basically, we've taken a set of 5 weights, the number of weights, start again. We've taken a set of 5 by 5 convolutional kernels. And, each of the patterns in each of these kernels looks fairly random. But if you look up and down this, all of the non-zero elements do not collide. We can then take these 5 kernels, and basically, because they're all the non-zeros are in different locations, we can overlay them, compress that into a single dense kernel, perform processing on that, and then split the results back out to the various subcomponents. And so, this is a particularly powerful technique because essentially what we're doing is we've taken 5 sparse kernels, we've compressed it into one kernel, so we should get a 5x speed up. The number of kernels we can compress is basically directly related to the sparsity of the kernels. This applies to both convolution and linear layers. So we should be able to approach a sort of linear speed up with the degree of sparsity. The only caveat being is you need permute support to basically separate out the subcomponents. Given that you need efficient permute support, we initially looked at implementing this on an FPGA. So we basically put together a performance demonstration to really showcase what can be done with sparsity. So we leveraged these complementary sparsity. We had these complementary convolutional kernels. We leveraged weight sparsity and activation sparsity at the same time and implemented this on a Xilinx FPGA. When we compared the performance of our sparse networks against the dense baseline that had been created using Xilinx's tooling, we saw significant performance improvements. For one network, sparse dense is sparse weights, dense activations. We saw a 10x performance improvement. For sparse, so sparse activations as well, we saw 30x performance improvement. And then basically we looked at full chip performance. We tried to pack as many elements, as many networks as we could onto the chip. Because the sparse networks are smaller, more efficient, less weight, you can pack more copies. And so the overall per chip speed up is about 50x from weight sparsity or over 100x from using both activation and weight sparsity. So you may be saying, well, that's great, Lawrence. You've demonstrated the FPGAs can outperform dense. How does this relate to other performance on other systems? So here I'm comparing it with a 24-core recent Intel Xeon processor. This basically maps to a AWS C5 12X large. And you can see here that the Numenta SD, that's the weight sparse, and the SS is the sparse in both dimensions. And full chip performance is basically, over 10x faster than a 24-core CPU. As I mentioned, there's nothing, intrinsically special about FPGAs. The efficiency of the permute operations there is a little higher, but nevertheless, GPUs and CPUs can also perform permute operations, and so we're actually extending this technique now to CPUs and GPUs. And initial results show that for a 95% weight sparse matrix, we can get actually an 18x performance improvement. In the interest of time, I will skip through this slide.
We have 5 minutes.
Yeah, the last slide, I'm just finishing up here. So basically, some cautionary notes. We've talked about the great things about sparsity, things to be careful of, right? And this really applies to AI writ large, right? never live just by a single accuracy score, right? You may say that the sparse network has equivalent accuracy to the original dense network, but there can be a myriad of differences under the surface. Really understand the accuracy across all of the subpopulations in your data. You don't want to get to a situation where basically you've got, significantly degraded accuracy across a population. So you're introducing bias and unfairness into that. This is especially true when you're interacting with models that affect humans, when you're looking at characteristics as gender or race or ethnicity or wealth or zip code. You really need to make sure that your model is fair and unbiased. And so in this situation, we're removing weights, we're creating these sparse models. It is necessary to understand what's going on, right? What are these fine-grained changes, if any, that are occurring as a result of this sparsity? And so it's important to really drill down and understand, as I said, the accuracy across all of the different subpopulations. There's a lot of research going on in this space at present. People are trying to understand, are sparse networks more susceptible to noise? What does their generalization look like? Are they more susceptible to adversarial attacks? And, research starting to indicate that basically a lot of the capacity of these dense networks is actually being spent trying to disambiguate sort of weird corner cases. And so when you sparsify the network, basically you may be losing the ability to actually sort of disambiguate some of these weirder examples that you have in your training set. And so again, it's important to look at all of the accuracy across each of the different subpopulations. So quickly now to conclude in the dying seconds of the presentation, we've talked about sparse neural nets. We've talked about reducing the number of interconnections between the neurons, which is weight sparsity. We've talked about limiting the neural activations, which is activation sparsity. It represents a key technique for reducing the costs associated with AI. Up to 100x can be achievable. That said, we're not at that point yet. When we're running on today's systems using weight sparsity, we're typically seeing somewhere between 2 and 4x performance improvements. Still, that's not bad. There's a lot of open source libraries out there for creating these sparse models. When you create the sparse models, remember to understand what, the characteristics of the new model, that it's still fair, that it's still unbiased, and then do stay tuned. I think that, in the coming, weeks, months, and years, we're going to see a lot faster, a lot more efficient sparse models out there. So stay tuned.
All right. So we have a networking session from 5:30. So very few minutes left. Okay. One question from Chong. Your first slide shows the book 1,000 Brains. I guess this is the theoretical foundation of your study. Can you tell us more about the book and how book is connected to your research?
Yeah, sure. So basically, Numenta was founded by a gentleman named Jeff Hawkins, who has really created this company to understand, how we as humans, how the neocortex delivers intelligence, right? We have this ability for great generalized intelligence, and 1,000 Brains is really his latest thoughts on how the neocortex does this, right? And so what the rest of us are doing there, working with Jeff to basically take his insights into neuroscience and then map them down into AI. As I said, sparsity is at the foundation of all of this. Without sparsity, the brain couldn't function as efficiently. We believe you need sparsity in AI to actually reduce the costs. But then there's a whole bunch of other aspects that we're looking at as well. How do you get continual learning? How do you avoid catastrophic forgetting? How do you do multitask learning? How do you get to the point with reference frames where you don't need so many training images? Basically, you can just show it a couple of images and it can start to build invariant models. And then finally, moving towards a sort of generalized approach to intelligence modeled after the brain.
That's a great tie-in with the book.
Yes.
We are out of time. And thank you very much for a wonderful presentation. I, for one, am going to be getting that book.
Well, thank you. I'm glad. I hope everyone enjoyed it.
Renway?
Yeah, thank you.
Thank you very much.
Thank you, everyone. Thank you for being the part of this year's DataCon LA. Thank you.
Thank you very much.
Bye-bye.
Bye.
We have plenty more tomorrow. See you.